Let me begin by wishing you all good morning and thanking the Howard Foundation and Alan Howard in particular for making this conference possible, and also, of course, John Nolan for his wonderful organization. I'm sure it's going to be an outstanding conference. There is my title slide, and as we've been told several times, 2 years ago, Paul Bernstein gave us all homework assignments, and this was my one, to continue to improve and utilize non-invasive methods of carotenoid assessment. And where's Paul? Paul, here is my homework. I'm handing it in. I expect an A. It's called the MapCat. It's an LED-based heterochromatic flicker photometer, and it incorporates some new features that we think make it much easier for the patient or the subject to use. And it's, I'll point out that it is downstairs, and I hope all of you will get a chance to get not only your macular pigment measured, but also your lens density, because it's it has more than just the function of measuring macular pigment. For the one or two of you here who maybe are not familiar with flicker photometry, this slide illustrates the process. In the upper part here, we have a stimulus which alternates between two wavelengths, one which is strongly absorbed by the macular pigment, one which is less strongly absorbed. Let's call those blue and green. And they pass through two absorbing or attenuating layers. First of all, the lens, particularly the aged lens, which of course, as you know, becomes yellow with age. And secondly, the macular pigment layer here, and then it impinges on the photoreceptors. And the subject has the ability to alter the intensity of either or both of the two wavelengths. In the machine I'm describing, we control the intensity of the blue. And the subject adjusts that intensity until the luminance of the two colors here are the same. And that's judged by an absence of flicker. We do a second measurement here where the subject views a peripheral target so that the stimulus is imaged in an area where there is no macular pigment, and so the only attenuator in the light path is the lens. So one would think then that in principle, you ought to be able to get some information about the light-absorbing properties of the lens from this second measurement, and from a combination of both measurements, you could subtract out the lens and obtain information about the macular pigment. So that's what the instrument does. When we first turn on the instrument, and when you first turn it on downstairs, this is what you're likely to see. In other words, it's going to be out of focus. There is a single lap unit, and you can turn that back and forth to obtain something that looks like this. And the stimulus at the center is 1.5 degrees in diameter, and it's identical in hue and luminance to the surround. And only the green part of the stimulus at this stage is illuminated. The overall luminance is about 20 candelas per meter squared, and that translates to a comfortable retinal illuminance of about 2.5 log trolins. So it's not going to blind you with too much light. Once we've achieved focus, we start the alternation between that green and the blue. And if the subject turns the control in the clockwise direction, the stimulus flickers like this and also appears to be brighter than the surrounding green. The frequency that we found to be best is 24 Hertz, but it is adjustable for the individual, and this means that we can use it in the so-called CHFP mode, which is called customized heterochromatic flicker photometry. If the control is moved the other way, we get what we call dark flicker, that it stands out as dark against the green surround. And then we tell the subject that somewhere in the middle, you're going to find a situation like this, where the flicker is minimized or disappears completely. And the other important thing is that it's equiluminant with the surround. So this equiluminance between the stimulus and surround at the match point provides a clue to the subject as to which way they should be turning the control. Why do we use a 1.5 degree stimulus when so many other devices use a 1 degree stimulus? Simply because, in my own experience, I found it to be easier with a more sharply defined flicker null than I get with a 1 degree stimulus. And I sometimes wonder if people have chosen 1 degree just because it's an interesting number, like perhaps E or pi. The reason I think we get a more sharply defined flicker null is because although you may try to fixate rigidly on those crosshairs, involuntary eye movements are going to cause the stimulus to move around something like this on the retina. And if you read the literature, you'll find that these involuntary eye movements tend to max out at about 0.5 degree, which is large in comparison to a 1 degree diameter stimulus. So the sampled area here is going to be considerably larger than the actual stimulus area. The percentage, if you express the sampled area as a percentage of the stimulus area, that percentage will be lower here if we have a 1.5 degree stimulus. So the variation in macular pigment density over this sampled area, that variation is going to be less for a 1.5 degree compared with a 1 degree stimulus. So that, I think, could be the reason why, at least I find a 1.5 degree stimulus gives a more sharply defined flicker null. I'll skip over that. Now, traditional heterochromatic flicker photometry, the second measurement involves an eccentric gaze position. And this basically was the problem that I was trying to overcome in the new design. Because what you have to do here is to gaze at the red fixation dot and then try to judge whether that flickering stimulus, which is now appearing in your peripheral retina, is flickering or not. And many people that you talk to say, oh, I find it very difficult to prevent myself from sneaking a peeked look back directly at the stimulus to see if it's still flickering. And of course, if you do that, you ruin the experiment. You're basically just repeating the first part of the experiment. And in fact, Gallagher and co-workers mentioned this in a paper in 2007 about the difficulty the subject had in maintaining fixation away from the parafoveal stimulus. The other problem is Troxler fading. And this occurs when you look fixedly at a point, and if your gaze is really steady, the objects in your peripheral field of view can fade away after a while. So I want everyone to look rigidly at the red spot and see if you notice this phenomenon, maybe. And then I'll ask everyone to blink. Oh, sorry. I'll ask everyone to blink, and it comes back into your field of view. But if you continue looking at the spot, again, it'll fade away. So those two problems make the second part of the test particularly difficult. So the inspiration for the new design came from this picture that in that wonderful book, Color Science by Wysecki and Stiles, and it shows the luminosity functions obtained with either a 2 degree field or a 10 degree field. And over on the long wavelength side, the two curves come together, but on the short wavelength side, you see that they depart. And because it's a logarithmic scale, basically the difference between those two curves represents the absorption spectrum of the macular pigment. And one could imagine that the maximum difference here is at 460 nanometers. So I wondered, well, I wonder if we make a flicker photometer that's got a small field and a large field, this would work. So actually, I extended it from 10 degrees to 15 degrees. And this is what the stimulus looks like away from the equiluminant point. So the entire field appears to flicker. We found that the optimum frequency here was around 30 hertz. Again, it's adjustable for the individual. And a remarkable thing happens as you can turn the control that controls the blue part of the stimulus. You suddenly find that it concentrates down, the region of flicker concentrates down to a small region around the fixation point. And the important thing is that it's steady around the periphery. And if you turn the control either clockwise or counterclockwise from this position, it starts to flicker everywhere, particularly noticeable around the periphery. So this would be equivalent to a small stimulus there with central fixation on the cross, so that such a small stimulus would be out at about 7 degrees. So my large 15-degree stimulus, I'm going to claim, is probably equivalent to a small stimulus viewed at about 7 degrees eccentricity. Nobody likes math. A friend of mine went to the dentist once. It was a new dentist, and he asked my friend what he taught, and my friend said physics. And as he bore down with the drill, the dentist said, "I hated physics." And this is why. Equations, but let's try and make it easy. So at the flicker null, we're saying that the blue luminance is equal to the green luminance, and that blue luminance is expressed on the left here. First of all, we've got the blue LED energy. Let's say it's normalized, but we've got an adjustable factor here for when the patient turns the control. If we multiply that energy by the sensitivity of the retina, the luminosity function, and then modify it by the transmittance of the macular pigment, then we get the luminance of the blue part of the stimulus. Same thing on the right. And I've expressed the transmittance of the macular pigment in terms of a density spectrum normalized to a unity at its peak. And P then would be the peak MPOD. That's the thing that we want to measure. For the second perifoveal measurement, the equation looks more or less the same, except we don't have the macular pigment because we assume its transmittance here is 100%. And because of that, the adjustment factor here is different. If we divide one equation by the other, we get the ratio of the two blue intensity settings that we make. And one could imagine that if we knew what the luminosity function was for the particular subject, we would be able to solve this equation and extract out the peak optical density, which is what we're trying to measure. I'll tell you how we get the appropriate V lambda curve in a minute. But anyway, what it means is, here's the relation, or the solution to that equation. And each of these curves would represent a different age, going, I think, from 15 up to 90 years. What it means is, oh, and let me just say in passing that if we use monochromatic sources, considerable cancellation occurs in this equation, and we get this well-known one here, which you will recognize. It turns up in many, many papers on measurement of macular pigment by HFP. Anyway, this log ratio here translates into the peak MPOD. For example, if we get a log ratio of 0.4 on a young individual, we come up to the curve across, it might mean that P was equal to 0.6, but the same log ratio come up here for a 90-year-old, go across, and it might be a value of 0.8. Conversely, two subjects having different ages might have the same peak MPOD here, say 0.6. The older person would have a smaller value of the log ratio, and a younger person come across here and down would have a larger value. And my graduate student, Anaban, will be presenting a poster in which he will point out the potential problem when we use HFP, particularly an LED-based HFP, and try to study the variation of macular pigment with age. I'll leave him to talk about that. So the question was, how do we get that appropriate photopic luminosity function? Well, we can get it actually from the perifoveal measurement, because in the equation which I've repeated here, if we measure the blue intensity and if we also measure the green intensity, then the only unknown is the V lambda function. But we should be aware that that V lambda function varies with age, particularly because of the increasing absorption by the lens. And Sagawa and Takahashi presented or wrote a very good paper on the variation in the luminosity function with age, and that allowed me to generate these luminosity functions. They're basically 10-degree luminosity functions for this different range of ages. So basically, the subject makes the measurement. They provide us with a particular intensity setting up here, and then there will be just one of these curves, which, when substituted into the equation, gives us a balance. By the way, that means then that we can know what is the effective age of the lens. And that's shown here by solving the equation. We plot what I call the lens equivalent age as a function of that ratio of blue to green in the perifoveal measurement. The MapCat provides us with this information. Here's a subject, 67-year-old, providing 5 repeat intensity measurements for both the 1.5 and the 15-degree stimuli. And the microprocessor calculates automatically the macular pigment optical density here. And many of you know that if you tell your patient or subject that they've got an MPOD of 0.4 or 0.6, they say, well, what does that mean? What we've done in the microprocessor is to use that number to calculate the average percentage of blue light being blocked by the macular pigment in the wavelength range 400 to 500 nanometers. So if you tell them blue light is damaging, but you've got 69% of it being blocked, they say, good, that means something to me. The instrument then also calculates the lens optical density, which I report rather arbitrarily at 425 nanometers. Again, that doesn't mean much to anyone, but if you tell them that the effective age of your lens is this much, that perhaps means something to them. In this case, 69 plus or minus 1 is very close to the actual age of the subject. So how well did the instrument perform? Something's gone slightly wrong here with the PowerPoint, but never mind. The overwhelming comment was that they found it easier with the larger stimulus. And this is very unusual, because most people say they find the peri or parafoveal setting harder to do than when they're looking directly at the stimulus. And this was reflected in the standard deviations of those sets of intensity measurements. So we looked at the standard deviation for the 1.5 degree set of data and the 15-degree set, and then we averaged for a large number of subjects. And as you can see here, just about, the standard deviation with the small stimulus was about double what it was for the large stimulus. We looked at the repeatability. So we did a test-retest, and this is a Bland-Altman plot of the difference between the test and the retest measurements as a function of the average. And we've got good results here. The mean difference was virtually 0, and the 95% confidence intervals were at about actually less than plus or minus 0.08. Slightly different way of presenting that data is just plotting the retest and against the test and looking at the correlation. We've got a very high R squared of 95%. Then we looked at the lens equivalent age versus the actual biological age, and people lying on the slope, the line of slope unity, will have a lens age which is the same as their own age. People lying below the line, Liz, for example, we tested her yesterday, have youthful lenses. People lying above the line, perhaps then they're not going to be quite so happy because their lens equivalent age exceeds their biological age. And is perhaps, by the way, a warning that maybe cataract is on the horizon. The instrument has been field tested in a number of ophthalmic clinics, one in San Diego, and the ophthalmologist there provided us with this data from his mostly older subjects. And when we plotted out the MPOD as a function of age, we got this negative correlation. And I think it was Randy Hammond found the same thing and postulated that maybe people having a higher macular pigment density is a reflection of overall high carotenoid levels in the eye, including the lens, where they could be acting, again, in a protective capacity and keeping the lens youthful. But then there's always a fly in the ointment, and when we did the same study in Miami with younger subjects, mostly younger subjects, we got exactly the opposite result. So what's going on here? My thought here may be that for this group of subjects, perhaps the older ones are starting to become more concerned about healthy living, improving their diet, eating more carotenoids, and increasing the amount of macular pigment. There I would then be assuming that the lens age is a surrogate measure of the actual biological age. And we have used the instrument just to prove that we can monitor successfully changes with supplementation. So we did a little trial with 10 milligrams per day of lutein for a 24-week period. And 2 subjects there had nice, robust increases compared with the placebo, where the line is essentially flat. So I think my time must be more or less up now. So let me acknowledge, first of all, Guardian Health Sciences and its CEO, Michael Favish, who was inspired by the first design of the instrument, which we see over here, and that led to this one that looks a little bit like a generator, and finally to this beautiful instrument here, which you'll see downstairs. And I, again, urge you to get yourself tested on it. Acknowledge Aniban, my graduate student, and then these 3, Jeff Morris, Howard Borger, and James Davis, who all had versions of the instrument in their ophthalmic practices. So they've put it through its paces, and we've made various refinements as a result. And finally, to Four Leaf for financial support. Thank you.
Thank you very much. So are there any questions for Richard?
Thank you for your talk. In fact, I have 2 questions, if I may. The first one is this V lambda. You say that's only dependent on, or that it depends on age of the lens, but couldn't that also depend on, for instance, the LVS MVS cone ratio? So could there be other factors which?
Certainly, there could be other factors. Certainly, but the two investigators, the Japanese group, in their paper, they attributed, at least on the short wavelength side, they attributed the changes primarily to the aging lens.
Okay. And then the other question is, you use this big circle now for the peripheral measurements. Can't you use it also for the central measurements?
In fact, you can. As you turn the control to increase the blue intensity, the flickering at the center, which is there, of course, because of the macular pigment, that gradually becomes less flickering. And so you find that you've got flicker around the periphery and a central region which is essentially flicker-free. But I've tried it myself, and of course I'm experienced at these things, but the huge amount of flicker that appears in the peripheral field is extremely distracting, and it's very hard to decide whether you've got a flicker-free region in the center. So it's much easier to use the small stimulus for that.
Okay, thank you.
Thanks.
John, did you say the green was fixed? Oh, Richard, I always do that every year. Did you say the green is fixed?
The green is fixed, yes.
Do you therefore notice a colour change? Do you notice a colour change?
No.
No?
No. We're in the periphery? Or?
No, for either, because it's for example, with someone with a lot of macular pigment, you're going to have to crank up the blue. And what I found when we had the old, we called it the independent mode, that we noticed colour change, and sometimes that got confused with flicker change.
The reason I have this particular system is that we find the equiluminance with the surround at the match point to be a good clue as to which way you need to turn the control to achieve that equiluminant point.
Okay.
I have two questions for you. Have you looked at a population that's had cataract surgery so that either has clear lenses or at least yellow tinted lenses, and how that affects, and what the equivalent age would be of a...
The equivalent age for a tinted lens, we've got very, very limited data on that, but turns out to be around 50 years of age. And for the clear lens, if I recall, it was around mid-20s.
Okay. And what you had I guess the first population versus your Miami population, were they drawn, was the first population drawn from clinical practices? Or
Yes.
Okay,
Yes,
so
clinical practice.
that actually correlates with, a lot of the controversy in whether macular pigment changes with age or not. A lot depends on how you select your subjects, whether it's coming from
Right.
clinical practices or research settings.
Mm-hmm.
So.
Hi, yes, thanks very much for your talk. And I like the design of the large spot, but we used to do work, certainly with DVLA years ago, when we measured fields, 3/4E fields, using a Goldman. And if you measure blind to seeing, and you plot the isopter, and if you measure the other way around, seeing to blind, you got a difference in the isopters. So trying to find a null point where you're actually seeing no flicker, I would suggest is much harder than seeing a point where you immediately see the flicker. And you remember the Macuscope? Remember the Macuscope, which was the previous device?
Unfortunately, yes.
Yeah. So, that particular point, trying to get an elderly person to tell you when there's no flicker, it's quite difficult.
Sometimes we find it's advantageous to take control of the instrument ourselves and to turn the control and move it and tell us when it becomes steady, and approach from both sides and try to bracket the position. But I don't know if you've tried the instrument downstairs, but I think you'll find it's not as hard as with some other instruments. And as I said, it may be because of the use of the slightly larger stimulus, the 1.5 degree versus a 1 degree.
Yep, certainly we'll give that a try. Thank you.
Yeah. And we'll hope that your lens is youthful.
From Scotland, no.
So I have a comment/question, and that is that one of the reasons that some of the machines yoke the green and the blue stimuli is that it creates this, and you're trying to do this, I guess, you're trying to create a different perceptual situation when it's on the bright side and the dark side.
Mm-hmm.
But the problem with that is that flicker is harder to detect on the dark side than it is on the bright side. The bright side, just the flicker is more visible because it's brighter. And that becomes worse, I guess, as you get older because your sensitivity goes down.
Hmm.
So what I found was that especially older people would have more confusion on the dark side. Mm-hmm. So it just became harder to see. So that made the flicker also harder to see. So that introduced a bias towards making their null point on that side of the stimulus.
Hmm.
So that was one logic behind yoking them to prevent
Right,
that artifact.
right. I can't honestly say that I've been aware of that problem in my own case. So perhaps some of the older people here can try it out and we'll get some feedback.